Okay, so in this video, we are going to talk about the continuity of fluid flow and Bernoullis equation. Okay, so now you have a pipe, and then you note that the diameter of the pipe here is larger than that here. Okay, so you say the velocity of fluid flows through this larger pipe is V1. The cross-sectional area of the larger pipe is A1. The cross-sectional area of the smaller pipe is A2. The velocity of the fluid that flows in the smaller pipe is V2. Okay, so you say that the mass of fluid flow in the larger pipe in a small time interval delta t is delta m1. Delta m1 equal to rho 1 times delta v1. Okay, delta v1 is a1 v1 times delta t. And then the mass of fluid flow in the smaller pipe is this one, the delta m2 in a small time interval delta t. Okay, and then you get this expression. And then now you assume that the fluid is incompressible. That is to say, the density of the fluid is a constant in everywhere within the pipe. Okay, you know that in a small time interval delta t, the mass of fluid flow in a larger pipe is the same as the mass of the fluid flow in the smaller pipe. And therefore, okay, now you know that the density is the same, right? Then you can cancel out them. And then delta t, you can also cancel them out. So you get A1 V1 equal to A2 V2. And then this is your equation of continuity, okay? And then this is only valid if the fluid is incompressible. Okay, and then actually you see the area has a unit of meter square, the velocity has a unit of meter per second, so this is meter cube per second. So this is like the rate of change of the volume. Okay, so the rate of change of volume, I mean the volume of the water, the fluid in the larger pipe is the same as the rate of change of volume in the smaller pipe. Okay, you remember this because we are going to use this right now. Okay, so Bernoulli's principle states that the sum of pressure, potential energy per unit volume, and kinetic energy per unit volume at any point in the fluid is equal to the sum of pressure, potential energy per unit volume, and kinetic energy per unit volume at any other point in the fluid. Okay, so in other words, you say that the sum of pressure, potential energy per unit volume, and kinetic energy per unit volume at any point is a constant. Okay, so you still remember that the work energy theorem? Okay, this is the work done, and then this is the change in the kinetic energy, and then the change in the potential energy. Okay, so now you have a pipe that looks like this. Okay, so the cross-sectional area of the pipe here is A1, and then the velocity of the fluid here is V1. Okay, so in a small time interval delta t, the fluid actually manages to flow from here all the way to here. Okay, so this is delta L1. Okay, and then work done by the pressure force onto the fluid in the tube is what? Is F1 times delta L1. Okay, F1 is the water pressure you feel at this point. Okay, the water pressure force you feel. Okay, so F1 equal to P1 A1. Okay, and then delta L1 is actually equal to V1 times delta T. Okay, and then this is the work done onto the fluid in the tube. The work done by fluid in the tube onto the fluid external to the tube. Okay, so there are some fluid external to the tube. The fluid external to the tube is here. The fluid external to the tube. The fluid external to the tube. Okay, I mean the pipe will continue. So the fluid external to the tube is here. Okay, so the work done by the fluid in the tube onto the fluid external to the tube is this one, F2 times delta L2. Okay, Then F2 is what? P2A2. Okay, delta L2 equal to V2 delta T. Okay, so the net work done is this one minus this one. Okay, and then you still remember that A1 V1 equal to A2 V2. Okay, A1 V1 equal to A2 V2 because this is the equation of continuity. Okay, so yeah, you know that A1 V1 delta T is equal to A2 V2 delta T, which is equal to delta volume. Okay, so you know that delta volume is the delta mass per density. Okay, and then you also assume that the fluid is incompressible, you know. That means that the density of the fluid is a constant along the streamline. Okay, the density of the fluid is a constant in any point within the pipe. Okay, so the change in kinetic energy of the fluid in the tube is delta kinetic energy, okay, which is half delta M times V2 square minus V1 square. So this is the change in the kinetic energy. And then the change in the gravitational potential energy is delta mg y2 minus y1. Okay, this is y1, this is y2. Okay, and then actually you know that the y2 minus y1 is height, right? Is your h. Okay, so you know that mgh is your potential energy, I mean your gravitational potential energy. And then okay, the work energy theorem is this one, right? Work energy theorem, and then you substitute everything, then you will get the Bernoullis equation. The pressure at point 1, okay, for example, this is point 1, okay, this is point 1, this is point 2, okay. The pressure at point 1 plus half rho V1 square plus rho Gy1 equal to pressure at point 2 plus half rho V2 square plus rho Gy2. This is what? This is your Bernoullis equation, because the Bernoulli principle states that the sum of pressure, potential energy per unit volume and the kinetic energy per unit volume at any point in the fluid is a constant. Okay? Okay, so actually this is pressure, right? This is what? Half mv square over volume. And then you know that mass over volume is what? Is the density. So this is what? This is kinetic energy per volume. Okay, mgh, I mean mgy is the potential energy, the gravitational potential energy. Mgy divided by volume is rho gy. Okay, so this is the gravitational potential energy per unit volume. Okay, you can also write the Bernoullis equation in another form, which is in this form. Okay, I mean the sum of all of them is a constant along a streamline. Okay, and then some people will say that, well, this is static pressure, this is dynamic pressure, this is hydrostatic pressure, or you can also say that this is pressure energy, this is kinetic energy, and this is your gravitational potential energy. Okay, but anyway, yeah, you know that the summation, okay, the sum of all the terms is a constant in any point in the fluid itself. And then you have to assume that the fluid has a constant density because it is incompressible. Okay, so let's do some question here. Show that the speed of the stream of water that comes out of a hole in one side of a container is this one, where h is the distance of the hole from the bottom of the container and capital H is the height of water in the container. Okay, so capital H is the height of the water in the container. Okay, and then the small h is the height of the hole. Okay, now you choose 2 points. One point is at the interface, okay, at the water and air interface. Okay, so you say that the pressure you feel at this point 2 is the atmospheric pressure. And then now this is a hole, right? You make a hole here. And then right at the hole, this is your point 1. And then because we have made a hole, right, so it is exposed to the atmospheric pressure. Okay, so you say that the pressure at point 1 is also the atmospheric pressure. So P1 equal to P2. Of course, you have to assume that the density of the air is very small. It's almost equal to 0. In fact, the density of air is like what? 1.225 kilogram per meter cube. However, it is still a very tiny amount compared to the density of water, which is 1000 kilogram per meter cube. Okay, so we assume that density of the air is like 0. If not, then you have to say that, well, P2 equal to what? The atmospheric pressure, and then P1 equal to the atmospheric pressure plus rho G. Okay, so this is what? This is maybe you say Y, okay, Y. Then, okay, yeah, rho Gy. However, we assume that the density of the air is like 0, so we ignore this term. Okay, so you say that P1 equal to P2 equal to atmospheric pressure, okay? Yeah, so you use the Bernoullis principle, the Bernoullis equation, okay? You assume that the hole is so small and thus the water stream is very tiny, so that the water surface moves down very slowly. So the velocity of water at this point is very slow. So you say that V2 is almost equal to 0, so you cancel out this term. And then you know that P1 equal to P2 equal to atmospheric pressure, so you can also cancel them. And then now you can cancel out the density. This rho is the density of the water, you know. Rho is the density of water. Okay, then finally you can say that, well, you already know the velocity, I mean the horizontal velocity of the stream of water when that comes out of the hole at this point. Okay, so I repeat one more time. The velocity here is actually the horizontal velocity of the water molecules at this point, okay? Because at this point it is not falling down yet, so the initial velocity in the vertical direction is 0, but then the initial horizontal velocity is given by this expression. Okay, so now we use this expression to answer this question. A water tank has 2 holes in each side. The first hole is 6 cm from the bottom of the tank, while the second hole is 5 cm from above the first hole. How deep is the water in the tank if the streams of water from the 2 holes hit the floor? Okay, this is the floor. You have some floor, okay? The floor. Hit the floor at the same point. Okay, so now you consider the vertical movement first. Okay, so that I want to know the free fall time for stream 1 and stream 2, because I'm going to use the free fall time in the horizontal motion. Okay, so now let's take a look at the horizontal motion first. Okay, because you know that the 2 streams of water actually hit the same point, so you know that the horizontal displacement is the same, S1 equal to S2. Okay, S1 equal to S2, the horizontal displacement is the same. And then you know that when you consider horizontal motion, they are moving at a constant velocity. I mean the horizontal velocity of the stream is v1, and then v1 is a constant throughout the journey. Okay, v1 is like this, is a constant. Okay, and then v2, which is the horizontal velocity of this water stream, is also a constant. Okay, because you assume that there is no air frictional force right now. Okay, so you know that there's no force acting in the horizontal direction. Okay, and then you know v1 and v2 because just now you have already derived the expression. but now you need T1 and T2 so that you can solve the whole question. So now we are going to find T1 and T2. So let's consider vertical motion, okay? S equal to ut plus half at squared. So the initial vertical velocity is 0, and then yeah, this term is 0. And then what is your acceleration? When you are in a free fall, your acceleration is the gravitational acceleration, which is the 9.81 meter per second. Okay, so you know that S equal to half gt squared. So for stream 1, T1 is like this, the time for the free fall of stream 1. And then the time of free fall for stream 2 is like this. And then you put them here. And then now you can say that, well, the height of the water, capital H, should be 17 cm. Okay. Water flows through a garden hose. Okay, this is a hose. Okay, this is a pipe that goes up a step 20 cm height. If the water pressure is 143 kilopascal at the bottom of the step, what is the pressure at the top of the step? Okay, so you know that 143 kilopascal is here. And then now you don't know how many pascal here. Given that the cross-sectional area of the hose on top of the step is half that at the bottom of the step, okay, so you know that A2 equal to half A1. And then the speed of the water at the bottom is 1.2 meter per second. Okay, now first and foremost, you assume what? You assume the fluid is incompressible, and therefore you can use the continuity equation. Okay, so you say A1 V1 equal to A2 V2. Okay, so you can find V2 for me. Okay, so now you use Bernoullis equation, the sum of the pressure and then the kinetic energy per volume and the gravitational potential energy per volume is the same along the streamline. Okay, yeah, so you substitute everything here, then you can know the pressure at this point 2. Okay, this point 2. Actually, point 2 can be any point along this pipe, you know. P2 can be here, 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 here. Okay, as long as you know that P2 is the pressure of the fluid in this pipe. Okay, in this section of the pipe, you know, not here, not here. Okay, but here only. Okay, as long as the area is a constant and then V2 is a constant along every point here. Okay, so in the next video we are going to talk about surface tension. Thank you.